Okay, so we've been talking about water in the atmosphere for the last week or so, and when you look at the page in the reference table, this is page number 14 here, the properties of the atmosphere. We have our temperature zones here, which you guys do understand at this point that that's what creates our different layers. That's what scientists said, hey, here's where the tropopause starts and the stratosphere begins, because the temperature swings. It was getting colder, now it's getting warmer. Then here it starts to get colder again, so we'll make this another layer and call it the mesosphere, and each one has its own properties. And then, without being too explicit about it, we've been talking about this a lot. We haven't looked at this and said, hey, this is what we're talking about, but we keep talking about dew point, relative humidity. That all has to do with water vapor in the atmosphere, so that's this little section right here. All the water vapor, most of it anyways, is condensed down in the troposphere, so that's where we're going to get all of our weather. And the next thing we're going to be tackling is air pressure, which is right here, atmospheric pressure. And you guys can also see that as we get down towards the surface of the earth, that's where we have most of that as well. Believe it or not, air has weight to it. Air molecules have weight to it, and because because the atmosphere is so tall compared to like a human, for example, we have 100 miles of air, stacked on top of us. It is pressing on us quite a bit. But you don't notice it too much because it's pressing on you from all sides. Plus, your skeleton is adapted to deal with the pressure of it without it being too distracting. But some of you may have experienced pressure changes with your body. I know that as I've gotten older, the injuries, we were just talking about injuries, the injuries I had when I was younger hurt more when we have low air pressure. So yesterday and today I'm just more sore than I would be on a couple of days before that, because the air pressure acts like a blanket. It's like pressing on your body, so it's keeping like your joints and like your tendons, your muscles kind of snug. Well, when the air pressure gets lower, when you take the blanket off of you, things inside your body have the opportunity to swell. And for people that have injuries, or if you just straight up get older, they will. They'll just take that opportunity because your body is a little more worn, it's a little more damaged from years of whatever you've been doing. So people may experience air pressure right from their bodies where they actually notice it. You guys may have noticed it too if you go up and down a hill. Like if you come up from Westfield or Ripley and you climb up the ridge, your ears pop because your body's stabilizing the air pressure in your sinus cavity to what's going on outside. It's just automatically doing that for you. So all that weight comes down to here. Now, believe it or not, the weight of the molecules, even themselves, plays a role here. So let this represent the ground here, and we're going to make this the tropopause up here. So we're looking at the whole troposphere right here. And yeah, this is not on your sheet yet. I just want you to stay with me on it. As air rises, so we'll make the air be purple. So as air rises in the troposphere, what will happen to its temperature? It's going up in the troposphere. You think so? Well, let's take a look. What does the data say? Yeah, it goes down. It goes down. Yep. So as we're going up in the troposphere, as air rises, it's going to get cooler. It has no choice. It's actually forced to get cooler. So it's going to rise and it's going to get cooler. And because of that, what's going to happen to the water vapor that's in the air?
It'll be more
yeah, it's going to condense at some point because the air can't hold it anymore. So it's going to reach a saturation point. So I'm going to make this be like an invisible dew point, like a saturation point where the air can't hold the water vapor anymore. So it's going to leave the water vapor behind, either in the form of a cloud, maybe this cloud actually precipitates, whatever. It's going to leave the water vapor behind. And then this is going to be free to be just dry air, air without water up in the troposphere. So you think, okay, it'll probably just go off into space again. But you know that this is a closed system. We don't lose air into space. So here's the thing that's really tough for people to understand, kids, adults, whomever. If I were to ask Google, which is heavier, nitrogen or water, because we know most of our atmosphere is composed of nitrogen and oxygen. So I'm curious, like, which one's heavier? You would think water would be, right? I mean, usually.
Water over air.
Yeah.
I think air.
You think air would be heavier? Do you?
Maybe.
Yeah, but most people say no. I think water's heavier than air. I mean, I picked up a bucket, a 5-gallon bucket with air in it before, and been like, wow, I'm strong. But I pick up a 5-gallon bucket full of water and carry it across my property. Yeah, and after only, a short amount of time, I feel good for about 30 seconds. Then I'm like, I don't know how to put this thing down because it's heavy. Yeah, water's heavy. But a water molecule is not heavy. Like a water molecule, H2O, is actually not heavy compared to, for example, nitrogen. So they're giving you molecular weights here, guys. You don't have to worry about the numbers so much. I just want you to see. It says water molecule has a molecular weight of 18. Free nitrogen has a molecular weight of 28. And oxygen, O2, has an atomic weight of 32. So we're talking about is quite a bit lighter. So what ends up happening here is that when you drop your water, you actually don't get lighter. It gets heavier because the same cube of air that had some water in it before now has nitrogen and oxygen, which is actually heavier, which makes it dense. It makes the air dense. So as the air kind of travels across the upper troposphere, it's too heavy. It's dry, but it's heavy. So what ends up happening is it falls down somewhere else and hits the ground. And this is what we call high pressure. And this, I'm going to make it red for a reason. We call this low pressure here. So low pressure air rises up in the atmosphere, rise, expand, cool, condense, and then it's the high pressure air is going to come down as dry air. Now, which rises in the atmosphere, guys? Warm air or cold air? Think about a hot air balloon. Warm air. So the reason I made this red is low pressure systems usually are full of warm air that has a lot of moisture in it. That's a low pressure system. Now, I told you that my injuries were kind of aching the last couple of days. So what kind of system do you think we have out here the last couple of days? High or low?
Low.
Low. Yeah, it is low. That blanket of pressure that keeps my ankle from swelling is gone. So my ankle, it's filled with like little fluid. I could feel it because I have like a really old, nasty ankle injury that it's not going to be able to heal properly. It was too wrecked. So, that we've had low pressure. What has the temperature been like? Warm or cold compared to like for our winter? What do you say the last couple days?
What's the day?
Yeah.
Probably colder.
You think so?
I mean, it feels like it.
I felt like it was.
It's a little. I don't know. There was like the first 2 days of this week. It was like it felt really cold.
Yeah.
15.
Yeah.
Today
It's not bad yet.
Right.
Today it's like
it's
almost
like
warm.
Yeah, right. So I would say, it's all a little bit relative because we're in the middle of winter here. But yeah, so we had I think on Monday on my way to work it was like 11 degrees or something like that. Yeah, and then yesterday when I was driving home from work, my temperature in the car said it was like 33. So this is relatively warm. Is it moist? Would you say it's like wet air out here, kind of? And don't think about precipitation. It's mean like when you walk outside, does it feel like damp a little bit?
Yeah.
Yeah, I would say. So it's like warm, damp air. This is low pressure, guys. Low pressure systems are usually associated with like lousy weather, meaning like it's warm, it's muggy, it's wet, probably going to rain. High pressure systems are usually sunny. There's the reason why. There's no water vapor in the air. This is a high pressure, like cool air just sinking down to the earth. It's usually sunny, but it's cool. It's cold. So we're probably going to experience some high pressure in the next couple of days here. The Buffalo Bills game is coming up. It's supposed to be very cold on Saturday night.
High pressure.
Yeah, high pressure playoffs. But yes, it's supposed to be chilly, and sunny too. If you look at the weekend forecast, it's supposed to be cold, but sunny. Because why would it be sunny? Well, if the high pressure system moves in, what you end up having is cool, dry air without much in the way of clouds, because there's no water vapor in the air. One thing about these guys, as this stuff rises up into the atmosphere, this one here, the low pressure system, it actually spins counterclockwise and in. It's hard to draw this. I'll just do my best. And then this one, that's a terrible, terrible arrow. There we go. This one here, when it hits the ground, it spins clockwise and out on the surface of the Earth. This will matter when we start looking at weather maps and other things like that. So, on your sheets here, where are we at? This thing here. On your sheets, I just want to see how much time I can see that timer. How do you see it though? Alright guys, we were just taking a second and looking at the weather, and I was telling the students in the room here that if I could look at one variable for weather prediction, I usually look at this black line here, which is air pressure, because I know if the pressure is high, that the temperature is going to be low, and there's going to be low chance of precipitation. If the pressure is low, the temperature will be high, and there'll be a good chance we're going to get some kind of lousy weather, snow or rain, or some type of precipitation. Okay, so on your sheets here, let's try to capture a little bit of this. So we said high pressure. So we have a little person here. So what I want you guys to do is to draw, if you have a blue pen or something, a blue highlighter is even better, but I want you to draw air coming down. And we're going to describe this air as cool, dry air. And when it hits down here by the person, it's going to spin clockwise and out. Clockwise. And the person here is going to be happy. High pressure days are usually associated with pleasant weather. Usually it's sunny. Usually it's comfortable. It's not very humid. The temperature is cool. They're usually days that people want to spend outside. Not so much in the winter, but definitely other times of the year. Okay, so a couple things about this. First of all, the spin on the surface, it spins clockwise and outward. And what's going on here? Well, we have cool, dry air sinking. Remember, we said it's sinking because it's dense, it's heavy. This is characterized by dry, sunny, clear skies. And this last piece here is going to become relevant to you guys as we start to look at how weather moves across the surface of the Earth. These move towards low pressure. And depending on how close a low pressure zone is to a high pressure zone, that's when you get the phenomena of wind, right? Because the high pressure will rush towards where the low pressure is. Where does this occur? Some of this will make sense to you, and some of it may not make as much sense to you just yet, but it will in time. So we'll cover this. I just want to restart the recording because we're going to run out of time on this one.